Yeah, now it is online.
Okay, thank you.
Can anybody check that it is?
Rakesh, please check that use YouTube.
For me, it is showing live.
Yes, it is live.
Okay, thank you, ma'am.
Okay. Good afternoon to all. Welcome to the 10th lecture series of the Radar Meteorology course, jointly conducted by South Asian Meteorological Association, Advanced Center for Atmospheric Radar Research, Cochin University of Science and Technology. Today, the lecture will be delivered by Thampi sir. He will be continuing from the last lecture where he stopped. So, I invite Professor Somesh sir to deliver the welcome address. Today, the lecture will be delivered by.
Am I audible? Is it okay? Can you hear me?
Yes, sir. Yes.
Okay. Thank you so much. Okay, well, good afternoon, everybody. ABM Professor Tyagi Saab, President of SAMA. Our today's distinguished speaker, Mr. S.B. Thampi. Dr. Pradhan Saab, Chairman of the Advisory Panel. Dr. Avilas, the main coordinator of the Radar Meteorology Lecture Series from ACARR CUSAT. Our organizing committee members, Dr. Swagata, Dr. Willy, Dr. Rohini, Rakesh. Good afternoon and welcome to the 10th lecture of this Radar Meteorology Lecture Series. As already informed by Dr. Avilas, Thampi will speak on the continuation of last week's lecture on very important topic about the different products of Doppler weather radar and their applications on weather forecasting. Well, last week you have already heard him, and all the audience is the same, speaker is the same, so I don't have to repeat the background of this lecture series, which was already told last time. I can only say that, well, today we will be completing almost half, or 50% of the lectures. Because we were planning about 21 lectures or maybe 22 lectures for this lecture series, and after today we will be completing almost 50% of the lectures. And I think there is a midterm test also in the timetable, if I remember correctly. There is a midterm test, Dr. Avilas, you remember?
So that we have not announced that yet, sir.
Okay. So anyway, it will be soon, maybe after 1 week or so, something like that, but it will be announced shortly. Oh, by the way, all the participants, many of you are members of the SAMA, and many of you are not the members of SAMA. You may know that SAMA will be celebrating its 5th Foundation Day on 3rd of August. That is next Saturday. It has completed 4 years. We complete 4 years on 3rd of August. And therefore, we already have a lecture schedule on 3rd of August that will have to reschedule probably on Sunday rather than on Saturday. 3rd August, we will have to reschedule the lecture on 4th August, Sunday. We shall formally announce it by email. All the members of SAMA will obviously receive the details of the Foundation Day celebration, but we can also share the information with the participants, even if you are not the members. In this week, we shall share all the detailed information. So, without delaying much, We can start today's lecture. Enjoy the lecture for today. And on to you, Dr. Abhilash.
Thank you, sir. Thank you. Now I request ABM retired Professor Aditya Gisab to deliver the presidential address.
Thank you, Abhilash, and I join Somesh in welcoming our speaker, Dr. Thampi, the chairman of the advisory committee, Dr. Pradhan, and of course, our dynamic secretary, Dr. Somesh, and of course, the chief coordinator, Abhilash. Along with that, all members of the organizing committee, they had been supporting these lecture series very, very efficiently as an excellent teamwork, I must say. And also, I think the quality of the lectures which are being delivered of very, very, very high standards. So that adds value to the all participants. I'm really happy that Dr. Thampi is continuing his second lecture on a very important aspect of the rainfall. You see, in the country, we are witnessing very heavy rainfall episodes in many of the cities, and this is becoming a feature. And there cannot be a better tool than the Doppler radar to monitor these and also to be used in the short-range forecasting and warnings. So this is a very powerful tool, which I'm sure with these inputs which are being provided by Dr. Thampi, all participants and students will be able to better appreciate the benefits of these weather radar, and of course the operational meteorologists and forecasters will apply his guidance and knowledge in their work. As mentioned that yes, idea of having the midterm exam is to ensure that you pick up these things, not just for the sake of that you attend a lecture and then forget. So you should benefit from these, and taking some sort of examination is a means to keep that in focus. So please, you've got YouTube lectures available so you can revise, and as and when these midterm lectures and the final exams are announced, appear with full sincerity, and I'm sure all of you will do well. So with these opening remarks, once again, thank you, Thampi Saab, to have delivering the second lecture, and I'm sure these are going to be very, very, very useful for all of us. Thank you.
Thank you.
Thank you, sir. Today I am happy that Sama's Joint Secretary, Dr. Mohan Kumar Das, joined, and he is our official photographer also. So I request Mohan to.
Thank you, sir. Thank you for the opportunity.
Maybe before going,
it is really a great initiative and excellent endeavor of weather radar for the meteorology and as well as the climate related activities. So all the prominent and very distinguished world-renowned scientists are delivering the lectures. It is really helpful to the not only young researchers, all kinds of professionals. So even it is a very good initiative that all the lectures are available in the Sama YouTube channel. Those who are not instantly or readily catch the lectures, they can check it again and do the work. Also, in the last executive coordination team meeting, there is one proposal like that. We will do some more initiative based on those lectures. So those lectures will be more popular in future. So thank you, sir. Thank you for the opportunity. Thank you, Thampi, sir. I've seen you after long days, after SMRC days. It is a good 2010. I think you are in the Doppler weather radar training course in the Kolkata. Nice to see you. Thank you, sir.
Thank you. Nice to see you all.
Today, our Radar Meteorology Advisory Panel Chairman Devendra Pradhan sir is also there. So, sir, you want to say a few words?
Thank you, Dr. Abhilash. Thank you, Thampi sir, Ajit Tyagi sir, Dr. Someshwar Das ji, and all other members. It's a great pleasure to see Dr. Thampi with us once again. In the last lecture, I could not attend because I was traveling. So it's a privilege to me and everyone here. So I welcome Dr. S.B. Thampi Saab, who has a long experience in the Doppler weather radars. And I would like to mention here that he is a person who knows each and everything in the hardware, software, and everywhere. And he was a person who maintained the Chennai radar, and not only the Chennai radar. When I was posted in Kolkata, he was helping me a lot in the maintenance of the Doppler radars at Kolkata, Visakhapatnam, and all other places. So I should say there is no one bigger than Dr. S.V. Thampi, more experienced than Thampi sir. So it's a really nice that we are having Thampi sir with us. And one more thing, Dr. Abhilash, I would like to mention here regarding the exams that we will give 2 weeks time to the participant, those who will be appearing for the midterm test here. And that will be objective type of the test, and all the questions will be taken from the syllabus, whatever have been covered so far. And as you have just mentioned that everything is available on the website in the YouTube. So all participants can join it, and it will be somewhere around 40 to 50 marks paper, all objective type. And hope that everyone should be able to understand. If before this, if there is anyone who wants to know anything from the our guest lecturers, they are free to call us and they can send our queries to us. So with these words, thanks Thampi sir once again for joining this lecture series. Thank you very much.
Thank you, sir. Before the lecture, shall we have a photograph? On Dr. Mohan, please. Ready? 3, 2, 1. Thank you. So now I request Thampi sir to deliver the today's lecture.
Okay. Thank you, sir. Dr. Somesh Das, Dr. Abhilash, Dr. Mohan Kumar, Dr. Devendra Pradhan, my friends. Thank you all for the kind and good words about me, though it is more exaggeration of what it is. Anyway, it's okay. In such occasions, it is very common to say hi of people. So I don't deserve that much. Okay, that's different. Now, let's go to the main part of it. That is the lecture. Last lecture, I covered basically briefly about the principles behind how the radar is working and how that is receiving the echo power, and echo power is converted into reflectivity factor converted into surface rainfall intensity converted into precipitation accumulation further converted into catchment area, and so many derived products and other thing. And during the question session, I saw many questions about that, how the radar derived rain and gauge derived rain are different, and they are not agreeing, they are underestimation, overestimation. A lot of questions were there. So I thought that today I will continue with that, the likely sources of errors, and each type of error, whether it will contribute to the overestimation or underestimation, briefly, maybe for 10-15 minutes. And then I will go to the second part of my assigned subject, that is velocity. There also, my plan is to just briefly talk about what is the basics behind that velocity estimation using radar, and from that towards the end, because there are many products based on velocity, I'll be putting a collage of different types of images on a particular day, which is having a lot of good set of data for visualizing all type of velocity products. And I will explain briefly, and I think with that we will be able to cover it. So without wasting time, I'm going to the lecture. That is, I'm sharing my desktop. Sorry. Show meeting timers. How to change the view? Speaker, gallery, show selfie, hide. How to minimize this view?
This is a PDF file, right?
Yeah, but this total seminar view is coming here in front.
Not going to the full screen.
Is it visible now?
It's visible, but it would be better if it is.
Yeah, I can. I want to increase its size.
And the back side, something is off. So,
I've closed this.
oh, yeah, now it is, yeah.
Yeah, now is it visible?
Yeah, yes, sir. Maybe view 100% or full screen.
It is visible anyway.
Is it okay now?
Yeah.
Yeah, I want to minimize this. Okay. Is
So
it
under view, there will be full screen, sir. Under view. Yeah.
Yeah.
Right side, right side. Oh, yes.
Is it okay now?
Yeah, right.
Okay. Sources of error in radar estimated rainfalls. So the error sources can be categorized into three types. That is errors coming in the estimation of radar reflected factor. Then second level is errors due to ZR relationship. And third one is due to the improper placing of the echoes as well as that radar rain aspect ratio and many other things. So that is the geometrical thing. First one is the science and second one is also science and third one is the limitations. So first set is coming under Z estimate errors or radar reflectivity errors. So one problem is that ground clutters. Ground clutters are echoes from nearby ground targets. We aim at the targets or hydrometeors in the atmosphere little above the ground, but because of the radar's limitation, radar power is partially or a little bit of is going on the side lobes also. Side lobe means main lobe is carrying the 99% of the echo power, and because of the geometry and the wavelength of the operating frequency, all these things, some of the energy escapes through the sides also. These side powers, though it is very, very small compared to the main lobe, they get reflection from nearby ground targets. These targets, if we convert that into rainfall, that is going to create a lot of spurious rainfall values. So they are generally filtered using many techniques. Modern radars are having a lot of techniques for filtering out the ground clutters. But one of the main method of removing ground clutters is that by seeing the statistics of the echoes, if there is no variance or it is very rock solid spectral pure power coming, so those echoes are called the zero velocity echoes. That much power will be removed. So by removing zero velocity echo power from the total power, we get rid of the clutter related rainfall estimate error. But one problem in that is there are places where the real rain echoes also would have zero velocity. In such cases, we will be inadvertently removing the real echoes, and that will create an underestimation of the rainfall. That is what is told here. That is ground clutter. The second one is anomalous propagation echoes. Anomalous propagation echoes are also a subtype of the ground clutter. What happens in the normal atmosphere, electromagnetic radiation propagates rectilinearly. But if the atmospheric temperature and thermal distribution is favorable, the electromagnetic radiation can bend, which will cause in the anomalous propagation of the beam which we are transmitting to the atmosphere. Instead of going in straight line, that can bend and bring ground echoes, or the buildings and trees and mountain, hills, all these things can come even from faraway places. In the general condition, the ground clutter problem is very close to the radar, maybe 5 to 10 kilometers. But in case of anomalous propagation case, even from 100 kilometers or 200 kilometers away, we can get ground clutter echoes coming. So it is a type of ground clutter, not only limited to the closer ranges of the radar, but also affecting the longer ranges. There also the same thing applies what we told about ground clutter cancellation. So that will mitigate the problem, but sometimes it will over mitigate, and that will result in the underestimation of the rainfall rate. Number 3 is, Number 3, partial beam filling. What it means is, we know with our present weather radar technology, we are operating in a frequency of the order of about 3 centimeter to about 10 centimeter, or even a little bit less than that. On those frequencies, the beam widens, that is, your spatial resolution is good, very close to the radar. And as you go away from the radar, the spatial resolution decreases, especially in the azimuthal direction. There we don't have a control. Every 60 kilometers, the beam widens by about 1 kilometers, or strictly speaking, pi, that is 57 kilometers or something, it becomes 1 kilometer. So then beyond that, if you are using the radar for estimation of the rainfall, if the echo or the events, weather events, thunderstorm or stratiform rain or something, if it is not completely filling the beam and the range gauge, if it is not filling, what happens? That echo receiver will interpret the received power as it is coming from the whole range bin, though it is not filled. What happens? Then it results in underestimation of rainfall intensity and overestimation of the rainfall aerial coverage. So the real beam may be 50% filled with a good intensity, but that will be shown as a full filling, that 100% filling with much less rainfall intensity. This is another error source. Next one is wet radome. Wet radome, see, when we are using 3 centimeter or 10 centimeter wavelength for our radar, then the parabolic dish which we employ for focusing the radiation has to be very big, maybe 4 meter or 10 meter, such bigger size dish reflectors are to be employed, and they cannot operate in an open atmosphere, open air, especially during heavy rain and wind condition. So to safeguard the system and make the driving system operate without any issues, we have to protect the antenna with a radome. Radome is a shelter for the antenna, which is transparent. Radome is supposed to be transparent for the electromagnetic radiation and protecting the antenna from all the vagaries of weather. So, but when it is raining and the surface of the radome, if it is having a film of water, or if it is a freezing rain or snow or something, a lot of layer of hydrometeor may accumulate over the radar surface, and that may attenuate the pulse power, and because of that, the radar will estimate the rainfall much less than what it is. So this is also wet radome causes the underestimation of rainfall. Next one is incorrect hardware calibration. Incorrect hardware calibration will cause significant errors in the rainfall estimate. The DWR estimates itself every volume scan, resulting in more accurate reflectivity and hence rainfall estimate. So a quantity delta syscal, that is how much is the variation of the present at the present moment calibration value and the already calibrated value. If it is exceeding plus or minus 2 dB, then the radar will warn you. Is one example I am giving. It need not be exactly plus or minus 2 dB and other thing. But when it is exceeding certain value, then the radar will tell you that you have to do something to correct the variation. Anyway, if there is a calibration error, maybe the power of the transmitter might have reduced, or some of the receiver sensitivity might have decreased, or the system noise might have increased. Because of all these things, there can be a calibration error. Because of the calibration error also, the radar may either underestimate or overestimate. In this case, both can happen. So all these things we have discussed so far is coming to the category Z estimation error or radar reflectivity estimation error. Next category is ZR relationship error. Last lecture, we have seen in detail why we have to have different ZR relations, how situation in atmosphere exists where the radar two sample volumes can give the same radar reflectivity factor but have entirely different or highly varying rainfall rate, and some other two sample volumes can have same rainfall rate but entirely different radar reflectivity factor. That is caused due to the different type of power exponential relation exists between radar reflectivity factor and the rainfall rate, as well as, of course, the echo power to radar reflectivity factor relation is proportional to the 6th power of the diameter of droplets, and rainfall rate is proportional to the 3rd power. Also, it is dependent on the fall velocity. Because of these things, as the drop size distribution varies, ZR relation can vary, but we live with a different type of ZR relations matching different situations and different geographic locations. These things we have seen in the last lecture in detail. Now, I am saying that how the variations are affecting the relation. Variation in drop size distribution from that assumed for the ZR relation can cause either an overestimation or an underestimation. Different drop size distributions can produce the same Z value. Yeah, that's what I told. Then mixed precipitation. There is another source. When rain is mixed with hail, snow or sleet, large reflectivity values results, causing overestimation. Bright band is another phenomena which already previous lecturers might have covered, that as we have seen, the radar reflectivity factor is proportional to the 6th power of diameter when it is in the Rayleigh region. But when the hydrometeor size grows beyond the probable drop diameter of maybe 3 millimeter, 5 millimeter, 6 millimeter, beyond that, it exponentially increases the radar reflectivity factor, and the situation which can cause such a higher value or anomalous or exorbitant value of radar reflectivity factor is due to a phenomena called melting hydrometeors. When snow or sleet or hail or something is falling down, once it crosses the melting layer, then the higher size hydrometeors may acquire a film of water coating over them, and one of the deciding parameter in the radar equation is that the dielectric constant of water is differing by a factor of 5 between ice or the solid hydrometeor and liquid hydrometeor. Because of this difference in the dielectric constants, just below the melting layer, there could be bigger size hydrometeors having a water coating which is having 5 times higher dielectric constant. Because of that, we get a ring of band of echoes around the radar, maybe which is matching with the freezing level on that day, just below the freezing level. This phenomena is called bright bands. This bright bands will definitely result in overestimation of rainfall in that band area. So this is an example of a bright band. Here a thunderstorm is there and a lot of solid hydrometeors. When they cross the freezing level, they are trying to melt, but they have not become droplets. Once they become droplets, the size becomes less. So further the radar reflective factor reduces. And over that, much above the freezing level, they have very low dielectric constant. Because of that also reflectivity is less. But in the region just below the freezing level, they have the bigger size as well as the higher dielectric constant. Because of that, we get a bright enhanced reflectivity. This is called a bright band. Why it is looking like a band and other thing, of course, I will not be able to cover here. Why it is around the radar, whether is knowing that there is a radar looking at that, and all those questions will come. Okay, that we will keep for some other time. Then below beam effect errors. Strong horizontal winds below the cloud base will displace the rainfall away from the ground below the range bin being sampled to below a totally different range ring. One example is shown here schematically. That is, if there is a thunderstorm and just below the thunderstorm there is a strong winds, then there are two gauges, gauge A and gauge B. Above the gauge A, if there is a radar looking at that space, it will report 50 dBc as something which is a very moderate or heavy rain. And this rain is expected to be falling and getting recorded over the gauge A. But because of that strong wind below, that gets translated to another location where gauge B is there. So above the gauge B, the radar will report 0 dBc, and above the gauge A, radar will report 50 dBc and corresponding heavy rain here and no rain here. And whereas the gauge will report heavy rain here and gauge here will report no rain. So such artifacts may come because of the space at which we are sampling the atmosphere. So radar samples at upper levels, whereas the gauge samples at ground level. So this difference, the wind will create all such problems. Evaporation below the radar beam is another problem. So it may rain at the higher, it may be raining here heavily, and if the air mass below that is it's a very dry air and a good wind speed is there, then by the time it falls down, a lot of air will evaporate. Virga type situations may arise, and that is one of the questions last time. So because of that, it is raining and radar will record, or it will say that over these points, because all the rain values are derived from the echo received from, because this radar cannot look down here like that. When it is rectilinearly propagating, it has to pass through the thunderstorm like this, and then this point value is taken to represent the gauge or space below that. So if the rain intensity is very good here, by the time it reaches the gauge, if it evaporates, then we will have an overestimation of rain by the radar, and gauge really will not get any rain. This is evaporation case. Then another important case where there is a overestimation, or the radar will report underestimation, gauge will report overestimation, is the case of coalescence. So below this, suppose the radar records the rainfall at this point, and if there is sufficient saturated air in the system below this, and as the droplets fall down, there could be a lot of coalescence, and the drops can grow further in their journey from this point to this point, and the gauge can get more rainfall. This is one example. These are briefly I touched upon what are all the possibilities, how the radar derived rainfall and gauge derived rainfall can vary. I think with that we will stop, and we will go to the velocity estimation and velocity products. All these things are known to all of you. What is Doppler effect? It is a frequency shift associated with motion. Examples are sound of train approaching and receding, redshift associated with expanding universe, measuring blood flow in veins, and police radar catching speeds, etc. Doppler radar is having an additional ability to measure both power and phase. What is phase? All of you know, and still I will touch upon in the subsequent slides. Weather radars do not measure the frequency shift within a pulse. Though we call this a Doppler radar is shifting the frequency. See, if we don't have any mechanism to measure the actual Doppler frequency, but only have a mechanism to measure how much is the phase of the received echo differ from one pulse to other pulse, or it is called as intra-pulse phase shift. Using that, actually it is nothing but a frequency means number of pulses. Here phase shift is within the pulse, how much is the phase changing. One pulse, one waveform, sinusoidal waveform is having 360 degrees. So we are confining our measurement to within a one sine wave. Within one sine wave, how much is the change? That is 0 to 360 degree or 0 to 2 pi radians. So whether Doppler radar will be able to measure only within that one sinusoidal wave. It cannot measure how many sine waves are passed between two pulses. That is why I am saying here, the ability is only to measure the phase. So again, what the limitation of a single radar is that radar is looking in one direction, then it can measure only the change in the direction. That is change of position of hydrometeors between two pulses in the direction of the beam alone can be detected by the radar. But the real atmospheric motion need not follow or need not know that there is a radar looking at them. So they are at random. They can move in any direction. But whatever motion is there in the sample volume will have a component in the direction of the beam. So what radar measures is the component of the real velocity in the direction of the beam. That is called the radial velocity. The convention is that radial velocity where the particles are moving away from the radar is positive, and when the particles are seen to be shifting towards the radar, that is interpulse path difference is towards the radar. If it is decreasing, the distance is decreasing with reference to the radar, then that is negative velocity. So a little bit of science, high school science, or a little bit of calculus. We can understand it with the calculus and without calculus. Both I will show you. How does the radar get velocity information on the particle? It's a very fundamental of the radar principle is that we are transmitting a pulse of radiation. So from here to here is a pulse. Then there is nothing. Then another pulse. Like that. Pulse by pulse, we are sending the energy. And the pulse is moving the atmosphere. It interacts with the hydrometeors or any other distributed particles here. An echo is created, or some of the energy is scattered in all directions. A part of that energy flows in the direction of the radar also. That part only is called echo. So this scattering can happen in all directions. It happens in all directions. A part is coming to the radar. And how much is the time difference between the transmission from here? That is when the pulse leaves the antenna, it goes there and echo comes in. So how much is the time taken for the pulse to go and echoes to come back? That is used as the measure of distance between the radar and the particle. So, but seeing in a more detailed way, we can also know that if you know how many pulses are there between the radar and the target, then number of pulses into wavelength also will be one way of knowing the distance between the radar and the target. The Doppler frequency is between one pulse to other pulse, how much distance the target has moved away or towards the radar. That is very, very less. When the order of frequency of radar is in the order of gigahertz or 10 to the power 9 hertz, the Doppler frequency is only in the order of about few thousand maximum few thousand hertz. That is why it is not creating, Doppler shift is not creating any error in the estimation between the estimation of the distance between the radar, because there is a coarse value. All of you know that for measuring any physical parameter, we will select a unit which is consistent with that distance. For example, for measuring the distance between Earth and stars, we use light years because it is so big. So the consistent unit is light years. If you want to measure the distance between one place, one city to other city in our country, we use kilometers. If you want to measure the distance between one end of the room to the other end of the room, we use meters. Like that, here for measuring the distance, we use kilometers or meters. That's range finding in radar is used in meters or kilometers. Whereas the interpulse phase difference between the targets from between one pulse to other pulse comes in the order of millimeters or even less than that. So there, this time difference into the velocity of light, that method will not work. This is a review of the waves. A sinusoidal wave is having a shape and it is having a phase. If it is a cosine wave, it is having at 0 degree or 0 angle, it will have a maximum magnitude and pi by 2. All these things are well known to all of you. So I am not going into that. But only thing we can express the distance either in wavelength or in phase also. The distance between this point to this point can be said as one wavelength lambda in centimeters or equal to 2 pi radians in degrees. Both way we can express the distance. So phase is with reference to one point. Here, if the phi 0 is the first phase, if it is 0, then after some time, if the pulse is reaching here, then we can say it is at pi by 2 and then 3 pi by 2 like that. So one pulse to the echo pulse, how much variation has happened in phase can be expressed in terms of phase difference. Now let us try to express the distance between the radar to one target in terms of this R is the range. Range is equal to in terms of distance R. The total distance D traveled by the wave is 2 times the R. The total of the wave cycles in the total distance is equal to total distance 2R divided by one wavelength. So that much number of wave cycles will be there in the total journey. Thus the distance in terms of radians, if you want to express it in terms of radians, that distance will be equal to 2R by lambda into 2 pi radians, because 2R by lambda cycles will be there. From this point to this point, if you count the number of times the field, electric field or magnetic field changes, will be total 2R divided by lambda. Or we can simply understand it as if you are using the wavelength as a scale, how many times we use the scale for measuring the distance. Just like our ruler in our geometry box or something, if that is having one wavelength, 3 centimeter, how many 3 centimeter wavelengths are there between like this? So that is 2R by lambda. Cycles will be there. That means cycle, and each cycle is equal to 2 pi radians. So this way we can express the distance. Then phi 0 is the phase of the pulse sent out by the radar. Phi is the phase of the returning signal. Then the received phase will be equal to initial phase phi 0 plus this 2R by lambda into 2 pi. That is 4 pi R by lambda. That will be the phase. Differentiating this equation, d phi by dt is equal to 4 pi by lambda into dr by dt, because phi 0 is the initial phase which is constant. So that becomes differentiating, that will become 0, and 4 pi is constant, lambda is constant. Only varying thing in here is r. So dr by dt is nothing but the rate of change of distance with respect to time is velocity. So how much the range or time derivative of the range variation is velocity. That is dr by dt. Take 2 consecutive pulses. So here we are trying to understand how it is arrived at. Take 2 consecutive pulses and measure the phase of the received pulse as shown in schematic here. d phi by dt is equal to, then the previous we have seen that d phi by dt is equal to, or rate of change of phase is equal to 4 pi by lambda into dr by dt. That is the previous equation here, this one. Okay. Where d phi is what? What is d phi? That is the phase difference. That is, we are sending one pulse and return echo is coming, and at some phase, then second pulse is coming and it is coming with another phase. So between these 2 pulses, how much is the phase difference? We need not know the original phase or the phase of the first one. So that is difference between the 2 pulse phases. Received echoes phases, one pulse and the previous pulse. The difference is d phi. And how much is the time spent between that? What is dt? That is the 1 by of PRF. That is, if you are sending 1000 PRF, 1 by 1000 is the time between two pulses. So 1 by dt is nothing but PR. So dt is equal to, that is nothing but radial velocity is equal to lambda by 4 pi, this one, into dr is what? Rate of change in the range is phi2 minus phi1 divided by dt is PRF. So maximum unambiguous measurable phase difference is 2 pi radians. This is the catch here. So we are in this exercise, we are trying to use the one pulse as to measure the interpulse path difference. By the time one echo is generated and by the time another echo comes to generate the echo, another pulse comes to generate the echo, how much the hydrometeor has changed. That path difference is phi2 minus phi1, and lambda by 4 pi into phi2 minus phi1 into PRF is the velocity. But if the path difference is exceeding 360 degrees or 2 pi radians, there will be an ambiguity. So when ambiguity comes, we will not be able to say whether it has one pulse has changed or the distance is one pulse or more pulse. We will not be able to say. So we have to design the scan strategy in such a way that for the existing velocity situation, what should be the PRF, interpulse time difference, so that the path difference remains within 360 degrees. So that is a maximum unambiguous measurable phase difference is 2 pi radians. So the maximum unambiguous measurable velocity works out to be Vmax equal to lambda by 4 pi into 2 pi into PRF is equal to lambda by 2 PRF. So this is the formula for the maximum velocity. But this velocity is to account for particles moving towards and away. Because in a pulse volume, there could be a streamline motion, kinetic motion, all possible velocity motions are there. Some of the particles may be having a component towards the radar and some of the particles motion may have a component away from the radar. So the system should keep provision for both. That is why the total Vmax is divided into two parts. That is plus lambda by 4 PRF and minus lambda by 4 PRF. This is the formula for Vmax. So this is using calculus and derivation and thing. But without that, a simple example I will tell you. Let's take a case here like that. So one pulse. This is a radar antenna. At time t1, it transmits one pulse. It goes and echoes are generated and coming back. Total distance is equal to del t, that is time delay between the pulse and echo into velocity of light by 2. Distance into velocity and by 2 accounts for the to and fro motion. So this is the distance. This 1 microsecond pulse, for example, is a typical wavelength, pulse width. So this pulse width of 1 microsecond, if the radar is operating in X band, say 10 gigahertz, a 10 gigahertz oscillator in 1 microsecond will have about 10,000 such cycles. 10,000 cycles. These 10,000 cycles, each one is of about 3 centimeter. So we don't go to that much high accuracy for our measurement. That's why generally we take the time taken from the pulse leaving and echo coming. That is converted into the range. General non-Doppler radars. But here, what happens? Let us have a fictitious, for our convenience, let us have a scale like this. It's a roller like this, which is graduated in wavelength, lambda, 2 lambda, 3 lambda, 4 lambda. The same in the previous slides, we have seen that how much waves are there in this one. If you count, then that into wavelength, we can also calculate the distance. So one wavelength is further divided into another subscale graduated into 0 to 360 degrees. Here, each degree corresponds to a few millimeters. So it is, so what we are interested is that from this, when the pulse has interacted with its droplet at this moment with the time t1, and after some time, t2, second pulse, So time difference between these two pulses is 1 by PRF. One pulse and next pulse. So this, after some time, the droplet, if it has moved, or in the direction of the beam, if it has moved this much, this path, this is called path difference. If the path difference is this much, then we need an accuracy of millimeters to know. Then only we will be able to get the velocity very accurately. So that is why in Doppler radar, though the total distance is measured using the time difference between two pulses, the interpulse phase shift is measured using the single pulse phase difference. That is, when the echo has come here at this receiver, the receiver notes down what is the phase of the received echo, phase. And it is a coherent source. That is, the oscillator which is creating this pulse is the same. It remains oscillating without any break. But the radar makes that power amplifier in the transmitter to amplify only for 1 microsecond or 2 microseconds according to the bit. The other time, the oscillator is continuing to oscillate, but that is not getting amplified and sent out. It is amplified, so the coherency remains. That is as if we are measuring the total number of pulses. But we are not bothered about this number of pulses here, but we are bothered about the last part of the scale. The last part of the scale, between when it was interacting at this first pulse and when the second pulse has come and interacted, how much path difference has happened, that path, it should be within 1 pulse. This should be within, this should not be more than 3 centimeter. Or 1.5 centimeter, because 1.5 centimeter for going and 1.5 centimeter for returning. So the total in a 3 centimeter radar, interpulse path difference of particles should not exceed 1.5 centimeter. So we adjust the PRF in such a way that our pulse repression frequency in such a way that interpulse path difference is within half of the wavelength. Then there are other methods how to, if there is an ambiguity happens, that is, if this 3 centimeters exceeds or for the given setup, if the particles move away more than 1 pulse, then how to decipher it, that is a different technique. I am not going to discuss that. So ultimately, we are finding the interpulse phase difference. And if you know the delta D in terms of phase of this two echoes, between the two echoes, how much is the phase difference? Express it in centimeter divided by the time. So it is high school geometry is sufficient that the distance traveled is expressed in degrees and time is known. If the distance and time is known, we can calculate the velocity. Here calculus is not required, and even Doppler concept also is not required. Without that, we will be able to understand the concept of radial velocity estimation. And now we will go back to the presentation. So we have found that B maximum is equal to plus minus lambda by 4 PRF. We know that this is about Doppler dilemma. That is one of the problem with which we have to live. That is, if we want to have a longer distance to be monitored, then we need low PRF. That is, maximum range is equal to velocity of light divided by PRF. When the PRF is lower, then we'll get a more range. Whereas maximum velocity, radial velocity, we can get if the PRF is very high. So between that, when you multiply these two, V max, R max, we get C lambda by 8, which is a constant, is called the Doppler dilemma. Then these things we will skip, and Doppler dilemma. Here this pink color, this magenta color plots the relation between the, PRF, pulse repression frequency, and the range. For a pulse repression frequency of about, say, 2000 meter, the range will be only 75 kilometers. Whereas PRF, if it is 1500, we will get about 100 kilometer. If PRF is 1000 meter, you will get 1000 PRF, 1000 hertz, then we will get 150 kilometer. And if it is 500, we will get about 300 kilometer. And if it is 250, we will get about 600 kilometer. Whereas for a 3 centimeter radar, when the PRF is 2000, we will be able to get up to 7.5 meter per second here. No, sorry, 15 meter per second velocity can be got, or interpulse phase difference will not be more than 1.5 meter when the pulse repetition is 2000. So this relation you can understand by looking at the graph. Now, coming to the interpretation of velocity product. For interpreting the radial velocity into the real velocity, we have to have some assumptions. What are the possible assumptions are? One is assume that the prevailing wind around the radar is uniform wind, or it is a linear wind, linearly changing wind. It may be convergence or divergence without any angular component for that. Only velocity convergence or velocity divergence, or there can be in some small areas a rotation can be assumed, like mesocyclone or tornado or something. There are small scale features as far as the radar is concerned. Then rotation, such things can be assumed. Based on the assumption, we can have methods of getting the real velocity from the radial velocity. This is one case of assumption of uniform velocity. This gray color things are real wind. Real wind happening, it is a west to east wind, or we call it westerlies. In the westerlies, if the radar is looking, it is sitting in a westerly field, and if it is looking, when the radar beam is looking in the direction of west, then it will see the full particles. Most of the particles are the radial velocity and the real velocity are almost same. All particles are moving towards the radar and it is negative velocity. And when the radar rotates and moves and looks in this direction, let us say, if it is looking in this direction, the wind is in this direction, the component of the wind in the beam direction will be reported by the radar as the radial velocity. Here the radial velocity has reduced. Here it is maximum. It is reduced here, further reduced. And in a perpendicular, when the radar is looking in the direction of north, and if the prevailing wind is west, we will get a zero radial velocity. In such situations, I told you that this ground clutter correction using the velocity, zero velocity algorithm, that will create problem in the rainfall estimation. Really, it is a set of particles moving west to east with a sufficient velocity and other thing, and it's a real rains, but the radar will report it as a zero radial velocity, and the clutter filter will remove the echo, and we may get underestimation in such cases. So when you have, there is a uniform flow and other thing, so in the rainfall estimate, we will have a line type of reduction in the total intensity. This is an artifact which we can find out and mitigate. Anyway, that is a diversion. Now, like this, when the wind is in one direction, the radar will see different magnitude of radial velocity, and when all of them put together, we get a pattern. From the pattern, we will be able to derive the real winds, provided our assumption of uniform wind is correct, or at least more or less agreeing to the real situation. Now, if we have only one radial velocity, we will not be able to arrive at the actual winds. So suppose there is a radial velocity reported here. We will not, this or any of this actual wind could have created this radial velocity. But if you have another point, another radial velocity coming here, then also this radial velocity could have been generated or is a result of any of these winds, a strong winds in this direction or a less strong wind in this direction, or really a wind this direction, or like that, all these possibilities. But if this one and this one has to coexist, both should coexist, then there is one possibility that the wind is westerly. So in this case, this radial velocity and this radial velocity, if both should be true, one of this uniform assumption if you take, then this is the real velocity. If it is linear velocity, there could be something. If it is rotation, something. It is divergence or convergence, it is something. So for the time being, let us confine our discussion with the uniform velocity only. So this is the case of the same thing, whatever deviates. So this is the strong westerly giving a maximum magnitude of radial velocity in the west direction and in the east direction. And in the north and south direction, the radial velocity is very, very low. So the values are marked here also. 0 knots is blue color, and plus 93 and minus 93. So again, the same thing is depicted. If the beam is looking in this direction, if the wind direction is northerly wind, if the radar is looking in the northerly direction, if the wind is, so then the VR is minus 20 meter per second. Here it is 20 meter per second. The actual wind will be reported by the radar. But if the wind is southerly, then it will be plus 20 meter per second, or actually it should be knots, not meter per second, 20 knots. And here it is, in this case, if the radar is looking northerly, if the real wind is westerly or easterly, both case, we will get radial velocity equal to 0. Now let us take one case. Here, this is a real image. So far, we were taking all, for convenience, some simulated values. And here it is a real radial velocity data. So this is on some classical one, 1997. So here, the radial velocity is maximum in this direction, maximum negative, that is approaching velocity, minus 40. Minus 40 meter per second is a unit here. So minus 40 here, and around plus 40 in this. So here the real wind is southeast to northwest. But the same thing, when the radar is looking in other directions, when the just perpendicular direction, then the radial velocity reported is 0, or white color is 0. So when we look together with the familiarity, and after seeing so much of images and going through these interpretation tools, we will be able to say that from this image that the real velocity is about 40 meter per second in the direction of southeast to northwest. So that is the total image put together will be able to or help you to decide what is the prevailing wind. This is more or less uniform wind condition satisfying. Otherwise, we will not get such a good depiction of the values. Now I will take an example. This is a Chennai radar, 2007, June 19th. This is a real data. From that data, I derived most of the possible radial velocity or velocity images. So they are, one is planned position indication velocity image. Planned position indication velocity, when you say that, you must be able to visualize that this is a conical surface. This is not a plane surface. So as you go away from the radar, you are looking at a higher and higher elevation of the atmosphere. So that is a PPI. PPI is a 9 degree. It's a cone with a 9 degree, 9 plus 9, 18 degree angle for the cone. And as you go away and away, you are looking at a higher and higher elevation. This is PPIB. This product is called VAD. VAD is velocity azimuth display. That is for a given range. Let us say 10 kilometer. From the data, every azimuth, let us say north, we'll start with north. North, what is the radial velocity value? Look at, say, keeping the range same, come and go on extracting the values of radial velocity all around the radar and plot it as a, and plot it like this. That is, this is north to east, south, west, and again north. So all the values. So here maximum you are seeing in this direction. There it's maximum, and the minimum is in this direction, negative values. That is here, and then here, and here it is 0. So when you take the radial velocity and plot it as a function of azimuth versus range. So given for the given range, azimuth versus the radial velocity, if you plot, that is called a velocity azimuth display. So the data is same. Here we are seeing a conical surface around the radar. Here we are seeing the radial velocity depiction around the radar for a given range. It can be a 10 kilometer or 20 kilometer or any kilometer of your interest. You can try it. In a uniform wind field, you will get a sinusoidal curve. Then this is a combination of two images. Whatever you are having in the behind, is that color, the filling the total image is the CAPI image. It is called the constant altitude PPI velocity image at a range of 30 kilometer. What was the constant altitude? Here, the surface is representing a curvilinear surface which is parallel to the surface of the earth. So it is not a plane, but it is the parallel to the earth. That is everywhere the distance from surface below and this point is given. It's maybe at what is a height 1 kilometer. This is atmosphere around the radar. 1 kilometer above the ground, what was the radial velocity? Here it is not like that. Here in this PPIV, as you go and away, the height increases. This is a 9 degree elevation. So 9 degree, very close to radar, it is 0. Then gradually height is increasing. But here it's not like that. Everywhere the height is 1 kilometer. That you have to see from the type of image. Then the range, what is the range? You can say 10, 20, 30. Even from the range ring, you can find out, or otherwise it is written here. And there are many other log values or metadata put here also. That also can help you. Then over that, there is another product derived using a uniform wind field that is called UWT, Uniform Wind Field Technique. So all these radial velocities put and some optimizing simultaneous equation solutions are derived, and from that the real velocity can be derived from the radial velocity. So such a derivation of the prevailing winds plotted as a surface plot is called UWT product, Uniform Wind Technique product. So here two products are there. One is CAPI product, CAPI radial velocity, and the uniform prevailing winds. And there is another product possible is that same technique that is using some solving simultaneous equation and minimizing some cost functions and other thing around the radar. The total data from lowest elevation to the highest elevation, all the radial velocity information coming from this small cylinder of data around the radar, maybe 20 kilometer, 30 kilometer, then we can solve the vertical profile of the horizontal winds. That is called, it is almost like our vertical time section plot of our radius on our pilot balloon. So here, this product has come from the radial velocity only. See, you are taking the scan from the lowest possible elevation to the highest possible elevation defined in the scan strategy, and all the data put together. When you submit the data to this particular algorithm called VVP, that is volume velocity processing product, then that will give you the vertical profile of wind like this. At the ground, it is about 5 knots, then 15 knots, 20 knots, 25 knots, and other things. So completely you can see the veering wind. Wind is veering with height. That is 0.3, 0.6 as you go and away, completely varying. So that varying can be inferred with some experience from this S type of 0 degree, velocity, 0 meter per second or 0 isotope. So white color, what is the shape of the white color around the radar? That is having a shape of almost S. This S shape of 0 isotope is a signature of varying wind with height. In a PPI, plan position indication image, not in this image. You should not look for the signature in this CAPI image. In a plan position indication with the height, the variation with the height is to be there. So here each point or each pixel is representing data from a different height. So this is in effect a vertical profile. So if the vertical profile depicted by a plan position indication velocity, if it is having a signature of S-shaped 0 isotope, then that is an indication of veering of wind, which is confirmed from the volume velocity product picture. So 1, 2, 3, 4, 5 type of products derived from a single scan data is depicted here. I think with this, we are coming to the end of the presentation. It is over to question.
Thank you, sir. I'm going for that. Sir, there is so many questions. I'm starting from one. Can you show one example of bright band seen in DWR?
Yeah, I can. Just a minute. Yeah. Are you seeing? Is it visible?
Yes, sir. Yes, sir.
Yeah, this is on 2005, October 26th, Chennai radar. This is a bright band. Also, you can see this artifact here. You see this one no data region. This is due to the clutter filtering. Clutter filtering removing the really the echoes are good echoes, but because of the clutter filter, that is clutter correction Doppler 7 is a very aggressive clutter correction. It has filtered out all the zero velocity. Actually, it's not zero velocity, zero radial velocity. Data has been filtered out. That artifact also can be seen. This is the bright band.
Yes, sir.
Okay.
Okay, sir. Next question is how to solve the overestimated rain due to the hail.
Due to the hail.
Hail.
Yeah, hail. If you know it is hail, then you can, with your experience, you can reduce it. Otherwise, there may be some algorithms which are giving the hail correction. That will all depend on the advanced products. Even some of the software providers may have a ready-made solution, or user groups who are having a research group working on this radar data can generate some of that algorithms and integrate with the existing software called Rainbow of Leonardo, or Iris of Vaishala, or Gamic. What is the name of that software? I don't know. Some Muran software. So they have one additional component called universal interfacing of customer products. So customers can come out based on their experience and their local topography and local climatology. They can understand how the products are generated from the raw data. And this hail, when hail is present, of course, there will be products of hail detection. When the hail detection is there, then what is the intensity of the hail and what is the size, all these things will be given by the ready-made products from the software. And taking them as an input, researchers can develop correction for the hail-related overestimation effect of rainfall. These are all the avenues available. But otherwise, if you are happy with the existing solutions, some of the softwares may be giving some generic solutions for correcting for the hail-related overestimation.
Thank you, sir. The another question is, how is the delta system calibration value taken as plus minus 2 dB?
It's not taken as plus minus 2 dB. That is, if the difference from the actual calibration to the present situation, we should have some margin. So even a small 0.1 dB, if there is a difference, if you want to correct it, it's not possible. But we have to give some, it can be, that is user definable. You can have delta sys can be even only 1 dB. I want to be very accurate. Even if data, if it is available, it should be good. So I can't tolerate 2 dB variation. You can set the delta sys as 1 dB or 0.5. Then there will be more occasion for you to interfere in the total radar calibration. More frequently, you may have to redo the calibration.
Thank you, sir. The another question is the Jadar gauze chalking. Do you limit the elevation height and distance from radar?
I could not understand the question.
Yeah, for Jadar gauge checking, do you limit the elevation height and distance from radar?
Yeah, that is, see, actually from the available data, we generally plan generic or mostly used scan strategies. For this particular season, for this radar, this is a scan strategy without any interference. It will take from, say, 0 degree to maybe 1 degree, 2 degree, 3 degree, 5 degree, 7 degree, 21 degree. Or if you want to have more number of revisit to the 0 degree, depending on situation, you can reduce the depth of the elevation. So anyway, based on the general strategy which is prevailing, data will be acquired and it will be available in the database. From that, we are generating the rainfall product. So if the data available is limited due to the non-visiting of particular space, for example, if you want to have your ZR, that is our surface rainfall intensity product, to have a distance up to 150 kilometers, then your scan should cover that region originally. If it is not covered, you will not get any data. So whatever is the data available, with that you can generate nominal surface. Generally, it is about 1 kilometer from the ground is taken as the surface rainfall intensity product. If with sufficient, maybe up to 20-degree elevation, if you cover, you will get a good coverage without much blocking. As the upper elevation are decreasing, then your central, very close to the radar data will be missing. So it is called the cone of silence. So the farther away products will be available from the lowest elevation. The closer to the radar data will be missing if your scan is not having that much depth.
Okay, sure. There is no more question in this question answer box, and I have checked YouTube also. No one has posted any question there.
Okay.
I think we have completed this question answer session, sir.
Okay.
Yeah.
Over to Abhilash, sir.
Okay. Okay. Thank you. Thank you, Dr. Miri, for conducting the QA session. Thampi sir, can you stop sharing the screen?
Yeah.
Yeah. Thank you, sir. So, yeah, thank you very much, Thampi sir, for delivering the second talk and elaborating on various aspects. Like you are putting the Doppler shift in a different way. That is very interesting to learn as well. And also different type of velocity products at different planes like PPV, CAPI, and velocity azimuth display and all. So it was a very wonderful lecture from you, sir, as always. And we are grateful to you, sir. And I request Somesh sir to have few comments or remarks.
No,
You are
you
muted.
are muted, sir. So, sir,
Is it okay now?
Yeah, it's okay.
Okay.
Yes.
So thank you so much, Thampi Saab, for a very interesting lecture. I'm sure that all the participants must have also enjoyed your lecture today. I mean, we can't have better speaker than Thampi Saab and Pradhan Saab, who have been really involved in the development of the radar products in IMD right from the beginning. So he had explained everything so clearly. Last time also he had explained, and this time also he had explained. So all of you, I'm sure that must have enjoyed his lecture. Those who could not attend, they can always refer to the YouTube lectures and then try to learn as much as possible. So thank you very much once again. On to you, Dr. Avilas.
Thank you, sir. I request Tyagi sir to have few words on.
Am I audible?
Yeah.
Yes, sir. Yes,
Yes,
yes.
sir.
Okay. So I also join Somesh in conveying our sincere thanks to Dr. Thampi. Let me tell all of the participants that please make full use of his both the YouTube lectures, and also I request Dr. Thampi that if his participants approach you, please try to guide them. And in long run, we will like to use this platform to develop some more advanced lectures on something new developments. So we'll make that also available with the guidance of Dr. Pradhan, Dr. Thampi. As of now, these 20 lectures will provide a solid foundation for both for students, researchers, and the operational meteorologists. So thank you so much. And Sama is really enriched by your two lectures. Thank you.
Thank you, sir. Thank you very much. Now I request Dr. Rohini to propose the vote of thanks.
Thank you, Dr. Abhilash. Can everyone hear me?
Yes,
Yes,
yes, yes.
Thank you. So first of all, I would like to thank the speaker, Dr. Thampi, So, sir, we are really happy and for this such an insightful lecture. Actually, Dr. P.N. Sain sir was also here few moments back, and he mentioned about you meeting you and all. So it was really nice to hear from him. So thank you, sir, again for such a nice lecture. And I would also like to thank him, Professor Ajit Tyagi sir and Professor Someshwar Das sir for giving the presidential address and welcome address. Definitely, without the support of these two, nothing, we won't be doing anything. So thank you, sir, again. And of course, Dr. Devendra Pradhan sir, who is handling everything about radar meteorology. So he's in the advisory panel also. Thank you very much. And of course, all the ECT members who are in the background, who are in the forefront, Mili Madam, Swagata, Dr. Mohan, Dr. Lakshmi Kumar, and all others who are not seen but are working for this lecture series. Thank you all. And definitely not the dynamic person, the moderator, Dr. Abhilash, who always is there. So thank you, Dr. Abhilash, and thank you, everyone.
Thank you, Dr. Rohini, for proposing the vote of thanks. And we will be meeting, Sir Somesh sir, we will be meeting on Sunday next time, right?
Sunday,
On
that
4th
is
instead of 3rd.
4th of August, yeah.
Yeah. So there will be a slight change in the schedule. We will send the mail soon regarding this, and we will announce the examination date, midterm examination date later. Thank you very much for joining, and have a nice day. Thank you very much.
All are invited to join the Foundation Day celebration of Sama on 3rd of August, Saturday, exactly at the same time, 3 p.m. Okay. So those who are the member, they will receive anyway all the details. I will request Dr. Avilas also to share the Zoom link with the participants who are not the members.
Okay.
They can also attend. So thank you so much. Yeah.
Thank you, sir. Thank you.
Thank you.
Thank you.
Thank you. Namaskar.